Water treatment plants have an understandably difficult job, cleaning dirty water that is potentially full of particulates, organisms, and other toxic chemicals. This process typically starts with the separation of these larger particles. The unit operation of choice would have to be the settling tank through the process of gravity separation. These tanks remove larger particles by slowing down the speed of the incoming water and letting the settling rates of the particles take over. While the process is simple, large settling tanks could be costly and take up unnecessary space. What if there was a more efficient way to do this while taking up less footprint? The answer is the Lamella Separator. Lamella separators have a very unique design. They use stacks of parallel plates set at an angle, allowing water to flow upwards between them, and they are known as inclined plate separators for this reason. You see, inclined surfaces, according to the boycott effect, decrease the amount of time to settle. Lamella separators work by forcing the water upwards through inclined channels to reduce the distance these particles have to settle. In other words, the distance between the two plates. All the while, they create large amounts of surface area for the particles to settle on. In fact, the efficiency of settling tanks depends greatly on surface area, which Lamella separators have plenty of. For Lamella separators to work, the settling velocity must be greater than the upward flow of water through these plates. Otherwise, the particles will simply flow out with the water. The direction of the forces sends the particle into the plate. Sediment begins to build on this plate until it flows backwards in the opposite direction of the flowing water. The sediment runs off the plates and collects at the bottom of the tank. To prevent any mixing, the flow between the plates must be laminar, so there is little water flowing at the edges. Particles with densities greater than the medium they are surrounded in will naturally sink. The speed at which particles stop accelerating is their terminal velocity, and it is super important in the design of the Lamella separator. You see, really small particles, we're talking about less than 100 microns here, exhibit more inner particle behaviors, such as Brownian motion. For these particles, terminal velocity, also known as settling velocity, can be approximated by using Stokes Law, a simplified mass balance where viscous drag and the force of gravity are considered. For this project, we assume our particles were spherical. Flocculant is often used as a pre-treatment option to make the smallest of particle sizes settle much faster. Particles in solution tend to develop negative charges on their surface, preventing natural agglomeration. Flocculants such as aluminum sulfate remove these charges by forming a bilayer and promote the formation of flocks, which are just multiple particles stuck together. Flocks are heavier than single particles, and therefore settle faster. Our project focused on making a small-scale prototype of the Lamella separator used in industry. By scaling down, we attempted to understand the forces at work with the tiniest of particles. We started off by creating the model in SolidWorks. Our design separator has 4 plates that are spaced 1.5 inches apart. They're angled at 60 degrees, which is a common industry standard. With this design, the total volume was around 17.5 liters. Holes were placed at the top of the channels so the clean water could escape without remixing. In addition, the separator was made entirely of plexiglass. The transparency of the material was very useful for observing the inside of the tank. We chose to use clay and sand as our particles, which are commonly filtered out of wastewater. Clay naturally has very, very small particles, less than 20 microns, while the sand we had purchased had to be ground in order to achieve this particle size. We ran the sand in a planetary ball mill for about 2 hours, and the result looked like flour. Both particles were now at max under 70 microns, which is much closer to the size for the Stokes flow assumption. The density of the sand had to be found experimentally. For better accuracy, the voids between the sand particles first had to be filled with water, as seen in this clip. Clay's density, on the other hand, was difficult to determine. The particles were too small, and the water couldn't diffuse without additional force. Literature values were used instead. Finally, the plexiglass plates were shaped using the laser cutter available to us. Here is the finished product. The Lamella separator was now able to be run. 2 solutions with similar concentrations of sand were made. The unit was filled 3/4 of the way with one of these solutions. Then a measured 4.1 liters per minute of solution was continuously added until it began to flow out of the holes at the top of the channels. This process was done until the second solution ran out, which was about a minute. A sample was then taken to be analyzed. The effects of flocculation were tested as well. We gave the flocculation some time to take effect and then repeated the process. After we had tested sand, we moved on to clay and we changed the flow rate to 2.78 liters per minute. This was to prevent washout because of the much smaller particle sizes. In the end, clay was a lot messier, but had the most striking results. In order to measure the efficiency of our separator, we employed the use of a very old UV-vis spectrophotometer. How does it work? In simple terms, the machine shoots a spectrum of light, usually around 200 to 1,000 nanometers, through a sample. The intensity that is transmitted through this sample is then recorded. The amount of light absorbed by the sample can give us a reasonable estimate of the concentration according to Beer's law. Different compounds will absorb different wavelengths of light, so it is important to take a baseline absorbance spectrum. Even if we can't visually observe the clarification, the spectrophotometer can. After gathering all the data and comparing them, we saw that our separator worked best for sand with no flocculant and clay with flocculant. The flocculant dramatically reduced the absorbance spectrum as expected, but the separator reduced it even more. After running a pass through the separator, the samples did in fact show a decrease in absorption, meaning the Lamella Separator we had made worked. In the end, our prototype showed some improvement of the water quality. Of course, this model was the first we had ever made, and the design could be optimized. But Lamella separators are already being used in industry. While they are not as common in the United States, they are widely seen in Europe's water treatment facilities. Hopefully, Lamella separators will be further investigated for their potential to clean water efficiently.